So today I'm going to talk about this issue in parametric mediation when we have multiple mediators, and I will focus on the situation with binary random variables. The assumption is that we have a recursive system of univariate logistic regressions, and they may arise in several fields like medicine, epidemiology, economics, and they may be used for describe some kind of complex systems. They may also arise as a longitudinal study with a binary response, which is measured at several occasions. I represent them as a directed acyclic graph, and as such, they allow a conditional independence interpretation. So this is the most complicated directed acyclic graph that you may think of, where we have k mediators. X is our treatment variable, maybe it's the variable we want to focus on, and Y is also the outcome we want to focus on. And the idea is to disentangle the effect of an external intervention on X, the effect on Y, and its possible decomposition through all these pathways. So again, the idea is that we think of an external intervention, whether it could be hypothetical or not, where we compare, and we want to compare the effect on Y by these by setting X, the treatment, to different levels. One small x compared with the baseline level, which I will denote with X star. I wanted to present data on this, but unfortunately we're really behind with these examples. But the idea is we have a kind of a treatment. We are dealing with the COVID-19 patients, treatment A or treatment B, whether there could be this treatment could have an effect on the probability of getting a pneumonia, and then these two together may influence the decision to go in intensive care, and this all together they may influence the outcome, which is surviving or not to the COVID-19. So this is a very simple example, much more complicated in reality. Obviously, there are unobserved factors which can influence the decision of going in intensive care and so on. So, but this is the basic structure of the problem. So the total causal effect is, again, we have a treatment taking two possible values, and we introduced the potential outcome of Y, which is the value of Y in unit I if exposed to the level X, and I will denote with this YI X in bracket. The same when instead of being exposed to the level X is being exposed to the level X star, and obviously only one of the two can ever be observed, and this is why it's also called potential outcome. The unit level causal effect is the difference between this value of Y under the two interventions, and is clearly intrinsically counterfactual. At the population level, we may want to assess the effect of the expected value of Y under this intervention and the expected value of Y under the second intervention. And we work on a population level effect, and we therefore drop the I in the following expressions. I know it's a very big jump, but we will do it here, and we don't have room for discussion. The expected, so we are interested in comparing the expected value of Y when X is fixed to small x versus the same when X is fixed to X star, where this is also counterfactual, because in this although to a lesser extent, here we are assuming that all units in my population are exposed to the same value X, whereas here all units in the population are exposed to the value x star, and we compare the average of these two population parameters. Now, the overview of the talk, I will speak about multiple causally ordered binary mediators, and I will focus for one mediator on the parametric decomposition of the effects without the rare outcome assumption, which is usually the one that is used. And I will also talk about the issue of non-collapsibility and the possible counterfactual interpretation of this problem, which is well known in the logistic context. I will also present the natural effect models, and then I will talk about the strategy, how the previous strategy for one mediator could be extended for helping in disentangle the parametric decomposition of the effects when we have more than one mediator, and draw conclusions. Now, a number of conditions are necessary to identify the elements of the total causal effects, and also, sorry, the total causal effects itself and its decomposition. We assume that the directed cyclic graph is structural in the sense of Pearl, which is a rather strong condition, can be weakened, but this talk will take it as a basic assumption. And again, I will not be concerned about issues on identification. So the basic idea is that with one mediator, we have, this is the directed cyclic graph, and the object is to decompose the total causal effect into an indirect effect, which is the red path, which is somehow transmitted to the mediator, and a direct effect, which is the green one, which is actually not involving W. And what do I mean by that? I hope it will become clearer later, because there are several different ways to do this decomposition. I will denote with this double crossing on the node W the operation where I'm marginalizing over this node, because to get to the marginal effect, the total causal effect is actually what I observe when I marginalize over the node W. And I will also talk about the encouragement design to visit museum. This is an experiment which was run in Italy, in particular in Florence, where the idea was how was to design an encouragement experiment to increase youth attendance of museums and to exploit the huge cultural heritage in the town of Florence. The encouragement design consists on 3 possible levels: a simple flyer, which is the basic level of the encouragement, which the context is we are within school adolescents, and we have around 200 students, each of them exposed to these 3 different possible levels. 3 different possible levels are considered. The flyer plus a sort of a detailed presentation of the museums, and the 3rd level is a sort of a credit prize if students go to visit museums. And we want to, all students are giving a free entry ticket to the Palazzo Vecchio. And the idea is we consider as the outcome the visit to other museums in the 6 months after the experiments. So the idea is to decompose the effect of the encouragement design on Y in one which is mediated to the visit to Palazzo Vecchio or into the direct one. We have several confounders, but the one which is really significant is what the students declare as a field of study, or as their preferred field of study, which is classified in basic, the level of humanities, which is the baseline level, or scientific, which is the other second level. Now, the issue of collapsibility is well known in logistic regression models. We suppose we have a model, a logistic model of Y against X and W. And we look at what happens in the marginal model when we marginalize over W. And we have two possible situations where X is influencing W, but also X is not influencing W, as in this second context. Well, in both situations, when you look at the marginal model, marginal logistic model, we know that this marginal logistic model is a very complicated function of the original model, and it's actually a non-collapsibility problem. And this is true if X is continuous. Actually, even if the original model is linear in X, the marginal model is non-linear anymore in X. And it's also true when X is binary, though in this situation we can perhaps understand it better because this has to do with the non-collapsibility of the odds ratio. We know that this coefficient here is the log odds ratio when you condition in the 2x2 table, when you condition on the level of W, and here is the log odds in the ratio in the marginal table. So in this second context, when X is binary, I always consider W also binary. There is a possibility to interpret the non-collapsibility, and I will show it later. So one mediator, direct and indirect effect. With one mediator, we need to introduce more potential outcome language. We have a Wx, which is the potential outcome of W. If X has been set to a small value X, we have the potential value of Y with two values because it depends on the value of X and the W value of W. We also need a potential to introduce a nested, let's say, notation where we need the Y outcome, which is the potential outcome when X is posed to X, but W is set to the natural it would naturally attain if X is taken to small x. And we need to compare, we also we need to introduce a sort of a nested counterfactual where this X here is different from this. And this is potential outcome of Y if X has been set to X, a small x, but W is free to vary and is free to take the value it naturally take if X is instead set to X star. This is a nested counterfactual, very controversial notion, and but somehow useful to disentangle this total effect into direct and indirect effect. And effects are a function of this, the probability of this counterfactual entity for varying X and X star. We also assume consistency, which means that whenever these two values of X are the same, this potential outcome coincides with the potential outcome when X is posed to X, forgetting about marginalizing over the W. So the very well-known counterfactual decomposition has been introduced by Robinson Greenland in 1992, and then later on formalized by Pearl, and several authors since then have worked on this. The total causal effect is the difference in expected value of the potential outcome of Y when X is equal in these two entities and is set to X, and the same when compared to the same when X is X star. The control direct effect is something which we already know is the expected value of Y when of the potential value of outcome of Y when X is let to vary, but W is fixed to a given value, small W.
This is the control direct effect with the usual well-known interpretation in statistics. The pure natural direct, we now decompose this entity, the total causal effect, by introducing these entities in red, which are a nested counterfactual, the potential outcome of y when x is set to x, but the mediator is free to vary as and to take its natural value if the exposure is set to x star. So the first, you see that in the first situation, you keep the mediator, the x star fixed, and you let this entity vary. And this is what is called the natural direct effect, because by keeping these, this effect is not mediated by W by any mean. And the vice versa is here, whereas you fix x for the purpose of y, but the mediator is sort of taking natural values under two different scenarios. The first where this x is equal to this, and the second is where x is to the exposure, sorry, to the baseline level. So this is the natural indirect effect, because x is fixed here, and all differences are due to the different values of the exposure, which varies for this distribution of the mediator. There is also a second counterfactual decomposition where you exchange the role of W or x and x star, and the interpretation is similar, but the W, what varies is what is the level here. For instance, for this is a natural indirect effect. So you keep y to for this part of y, the x is set to the baseline, and you let the mediator to take different values. In the first one, the natural value under the when the exposure is set to x, and in the second, then the natural value when the exposure is set to the baseline. This is also called pure because the baseline level, y is set to for this purpose at the baseline level, which is y is called the pure. It doesn't contain other effects, but what happens at the baseline, beside what happens at the baseline for the y's. And the vice versa is for the total natural direct effect. So here you let x varying, but you keep w to the natural value it would attain if the exposure is set to x in both scenarios. Okay, the similar decomposition, you can have it for the log scale. I'm not going to represent the concepts because the idea is exactly the same, is the scale that varies, and we measure it's measured on the log odds scale. So the total causal effect is the log odds. I just expressed this too. Is the log odds when these x are equal against the log odds of y when x is at the baseline. The control direct effect is when you externally fix the w. And then you have, again, the pure natural direct effect and also the other decomposition. And I'm not going to explain this in details because, as I say, not much changes about the previous comments apart from the scale. Now, when you deal with binary outcome, there is an issue which, because a number of non-parametric methods have been proposed, and a lot of literature on the way to disentangle the total direct effect, the mediation, in a mediation context, using non-parametric methods. Actually, this is interesting, but not doable when x is continuous, and the dimension of the confounders you need to condition on in order to achieve this assumption of the directed acyclic graph to be structural is very high. So for these reasons, we have authors that have provided the parametric decomposition of the log odds, but this decomposition is based on the rare outcome assumption, and it's not easily extended to multiple mediators. So here I'm presenting a strategy where you don't rely on the rare outcome assumption, and you may extend this is a parametric strategy with rather easily to multiple mediators. So I am posing two logistic models, the y on the y against x and w, and these are the beta parameters. The beta parameters, remember, they're always related to the logistic model of the outcome against the x and the w. Whereas I'm also using I'm also imposing a logistic model of w against the x, and the gamma parameters relate to the this second model. I'm also allowing interaction terms, which is something which is somehow excluded in non-parametric methods. And the question is, what is the parametric structure of the marginal logistic model? I mean, the one which is obtained after marginalizing over W. And this is a well-known result from first principles of probability. We know that the marginal logit is equal to the conditional logit plus the log of the relative risk of W when y varies in the distribution of x given x, in the condition distribution of x. Now, the problem is that we don't have a model here for this. We have a model for the marginal w against x. We do not have a model for w against y and x. So how can we work it out? Well, by repeatedly using the previous derivations, this time applying to the w variable, because I assume that the w is a binary once again, and so I can use it again. And this is the original model, where the outcome model, and here you have the marginal model. So here you have a sort of your logistic model for w, when y, depending on y and x, which is a function of the original model, and this is also the function of the original model. So if you put the pieces together, you can write the logistic model for w against y and x, and you may simplify this, getting this expression, which is the first bit is a function that comes from the outcome model because it contains the beta. Whereas this bit here is a function of the w against the x. So if you put pieces together, you may arrive to a parametric formulation of this marginal model, where here you have the log of relative risk of w equals 0 when varying y in the distribution of x given x. Taking the difference, we find the parametric expression of the marginal effect, and addition of covariates doesn't strongly alter the structure. Now, this is nothing to do for the moment with causality. This is a parametric structure when you impose a model on y and x, and some considerations. If you change the arrow from w to x instead from x from w, the expression of the marginal model doesn't change, and only the interpretation does. So just coming back to the total causal effect and the control direct effect, the total causal effect is the difference between the two models, the marginal models, in x and in x star. And here you have the log RR, which is the term that comes out from the marginalization over W. And obviously this log RR is making use of this GY structure, which is the one that I just derived as a function of the original model. The control direct effect, there is no new novelty, is clearly depends on W, and especially if there is an interaction term.
Now, remember that the counterfactual effects, they arise by crossing two possible worlds. In one, you are sort of conditioning to X star for the purposes of W, whereas in one, you are conditioning on X for the purposes of Y. So the question we are now posing is, can we cross it and do it parametrically? Because if you look at this 2x2 table, you have 4 terms, and on the main diagonal, you have the observed quantities, the usual ones, and off diagonal, you have elements where you are conditioning on X instead of X star for one or the two. In particular, the element C is leads to a function of Y in X star for the direct effect, and W for X in X for the one that is transmitted to W, and the vice versa is for the B. So the idea here is, can I expand the GY function by just simply making it a function of two different values, X and X star, and like here, where for the purposes of the direct model, I condition on X, whereas for the purposes of the W model, I condition on X star. And it turns out that if you do that, then it's a natural way to derive the parametric expression of the natural direct effect and the parametric expression of the natural indirect effect, which are clearly a function of these G, X, X star functions. Now, the expression I present here can be simplified further, and this is what we did in a paper that's been published already. Now, the idea, the important take-home message, I think, is that if you look at the natural effect model, which has been introduced in the literature, and it's been used for several purposes, not least the inverse probability weighting when you have more mediators. Well, the derivation, the implication of this, the previous derivations, that the natural effect model here is by construction proportional to this expression here, where you have here is the direct effect, this X is the direct effect, this X is the same here, and the X star is the one that concerns the W distribution, the distribution of W again X star. So this is a natural effect model which is derived coherently with the postulated data generating mechanism, and the link function is unchanged, but the right-hand side is non-linear, neither in X nor in X star, which is an interesting, I think, message. So the next step is, can I reconcile the classical path analysis methods with these with these counterfactual methods? Is there a link between the path analysis method and the causal effects? And here I will first of all present the usual way to define path analysis effect. The total effect is the same. The indirect effect is the indirect effect when there is no arrow between X and Y. So they are independent given W. And the direct effect is the direct effect is the effect when actually is the vice versa. There is no arrow between Y and W after conditioning on X. There is no direct arrow from W to Y. And it turns out that if you do this decomposition, the total effect is equal to the sum of the direct effect, the indirect effect, plus this residual term, which is actually the one which is responsible of this non-collapsibility. And just to remind, this is, if the data generating process is this, the total effect is the indirect effect. Whereas if the data generating process is like this, the total effect is the direct, this is the indirect effect. This is the direct effect, which is the coefficient beta x. Whereas in these two situations,
the residual is 0. In this situation, the residual is 0. And also in this situation, there is residual term is 0. However, this residual term is non-zero whenever you have two arrows pointing at y. So in this situation, is non-zero, but also in this situation is non-zero. And this is what is well known as a non-collapsibility effect. Remember that in a linear system, this residual term is 0 because the marginal effect here is always equal to the conditional effect as soon as these two are marginally independent. So let's look at this and try to reconcile the effect, the path analysis effect with the causal effect that I already introduced. And it turns out that if you do that, the indirect effect is the pure natural indirect effect, which is the one introduced by Robbins. When you sort of condition for the direct purposes, you leave 0, you leave x to the baseline level, and for the indirect, you let the mediator to take its natural value under 1 and compare to the same when actually the mediator is also on free to take its natural value under 0. So this is the indirect effect is actually a pure natural indirect effect in the causal framework. And it turns out then, as a consequence, also the residual has a sort of counterfactual interpretation, because remember that the pure natural indirect effect and the total natural direct effect, they should sum to the total effect. So if you do that, and indeed, if you look at the expression, you see that this is actually the direct effect of, the potential value of y when x is set to 1 on both the direct and through the mediator, minus the control direct effect, the beta x, let's say, what I call the direct effect in the path analysis context. And this is this is non-really counterfactual, but actually the counterfactual part comes here, because in this second term, you are conditioning on 0 for the purposes of the direct effect, and conditioning on 1 for the purposes of the indirect effect, the one which is mediated by W. And so it turns out that the residual is the component that you need to add to the control direct effect to obtain the total natural direct effect. So what is once again, the total natural direct effect is the direct effect when the mediator is free to achieve its natural value under x star equal, x star, this should be x, when x is equal to 1. So that's the total natural direct effect. So with this in mind, we could give some insights on the issue on non-collapsibility. And I here present the well-fitting regression models for the encouragement design. And these are basically the results. I keep an eye on the timing. So these you have remember you have three possible scenarios: the baseline intervention, the intermediate, and the most extreme, where students are also given a sort of a prize in terms of credits points. And this is a well-fitting model. And also this is for performing the visit to Palazzo Vecchio, and you see there is an increasing effect in the performance in going to visit Palazzo Vecchio, with the third, the most rewarding, having the highest effect on the probability of going to visit Palazzo Vecchio. Then you have the y against all the covariates, and they're all positive, but remember there is an interaction term which is negative, meaning that for students who are interested in mainly scientific, they are more likely to go farther, to perform further visits to other museums. even if they've gone or not gone to Palazzo Vecchio, sorry, but there is an interaction here which is sort of moderating. So what I said is wrong. So there is an effect of on why, if students have performed a visit to Palazzo Vecchio, which is also positive, but actually there is a moderating effect, a negative interaction. So if they're interested in science and mathematics, and they also visited Palazzo Vecchio, their effect on Y is not just the sum, there is a negative moderation effect. Okay, with this in mind, we can now interpret this residual term, which is the one that we wanted to focus now, because we have a direct effect, which is the effect of the second level of the treatment when compared to the first one, and we know it has a direct effect, a positive direct effect. Let's focus on this first, and then we interpret all the others because they are similar. There is an indirect effect. You see, this is the indirect effect, which is mediated by the W, which here is not significant, but later on it is significant. So it's good to interpret. This is the effect which is due to having gone to Palazzo Vecchio. So this is what is due to the mediation of the visit to Palazzo Vecchio. Then there is this residual term, and remember that these three, they sum to the total effect, which is actually positive. So the total effect is positive in all the four scenarios, and also significant. What is this residual? Well, if you remember, this interpretation is the amount you have to add to the direct effect, and when you let it free to vary and to take its natural value under the second scenario, because this is the interpretation of the residual. Now, these two together, they give you the natural direct effect. And since we don't have an interaction in these previous parameters, remember, we do not have an interaction between between the humanities and so on. Anyway, this is, we don't have an interaction between W and X in the outcome model. The direct effect is also is not only the direct effect in the baseline level, but is also the direct effect in the second level of on W. So for W equals 0 and for W equal 1, the direct effect is the same. So these two, they sum to the total natural direct effect. And it shows here, you can see that also this total natural direct effect is significant all the times. And you have this residual is negative in all possible scenarios. So this is perhaps a way to reconcile the usual classical path analysis framework with the causal inference context. Now, with more mediators, the formula of the marginal model can be generalized to more than one mediator. It's a bit complicated, but not very difficult once you understand the mechanism. And now I give you an example with two mediators and then draw conclusions. Suppose that we have a treatment, W is a side effect. One could intervene on W2. Let's think of the intensive care units of the previous example. And then we want to assess what is the best possible strategy. With two mediators, we have more potential outcome. And here, obviously, it's a bit complicated, but the extension is straightforward. And we have the usual interpretation when you have a WX and W2 is a function of X for the direct effect, and W1, the first mediator for the purposes here is the usual interpretation in terms of natural direct and direct effect. But here the things are a bit more complicated. And it turns out that you have for each type
of path-specific effect. You have 8 possible combinations depending on the value of the other variables. And this is what has been explained very clearly in the paper by Daniel and co-authors. Okay, and the issue here is can we derive the natural effect model in the similar fashion of the previous ones? And it turns out that you can do it in 2 steps. In the first one, you marginalize over W2. And by doing that, remember that here you have the W is a source node for this effect here, and is also a source node for this effect here. So you have to take that into account. It's not a rather straightforward way to do it. But then you end up with a model with just one mediator, and you repeat the marginalization. So here you have the expression for that, which is not really very easy. It requires a bit of derivations, but the idea is again to expand this function, which now I call H, into 2 terms, H X and X star, and you can do it, and then you can interpret this, and you repeat it, and you arrive to the nested counterfactual model, natural effect model with 2 mediators. Okay, so open issues derive also when you have 2 mediators. It will be interesting to derive the finest possible decomposition by meaning, what do I mean by that? Well, I mean something which relates the direct effect, indirect effect, and the residual which comes out from this non-collapsibility, and use them to describe the effects of hypothetical interventions, which could be something more complicated than a simple intervention on just one X. You can think of X, a strategy where we want to intervene on X, but also on one of the mediators, like in the examples that I gave at the beginning. So that we can be interested in a mixture of natural effects and path analysis effects. Final conclusions: the knowledge of the parametric structure allows insight on the effects and permits to deal with outcome. Also, I haven't talked about this for lack of time, but I can show that it also, when you have outcome-dependent sampling, you can solve your outcome-dependent sampling strategy. You can disentangle as well the effects you're interested. Rather straightforward attention to ordinal categorical data. And addition of covariates can be made in a rather straightforward manner. And obviously, sensitivity analysis against the identification assumption should be performed. And there are a very clear indication of that in the paper by Daniel and co-authors. List of references, the well-known references by Judea Pearl, VanderWeele. Obviously, this is the paper which I published with Marco Doretti on Biometrica, the Daniel and co-authors on biometrics. And this is where we present the exact parametric causal mediation analysis for the context I dealt with. For those of you who are interested in the issue on dropping the I in the discussion that I did at the beginning, there is a very nice paper with a very nice discussion by Kua and co-authors, which has been published on the Annals of Applied Statistics. And I also, the path analysis effects have been presented on this paper on sociological methods and research.